Hi, I'm Ahmed Daud, and in this session we will see overfitting and underfitting. Okay, in the last session we have done polynomial regression, in which we have seen how we can why we need actually polynomial regression or polynomial models, nonlinear models, and we also have seen how we can implement polynomial regression. Like if I will show you here the code, yeah, we have implemented here linear regression also, and we also have seen how we can implement polynomial regression. Is exactly the same that we have to implement linear regression, just we have to convert our features into some polynomial features before that. Okay, now keep in mind here the data set that we are using is very small data set. If I will show you here, yeah, this one, just six data points we are using here, and we are testing we are training our models on these six data points, and we are uh, getting prediction from again these data points that we have used during our training process. Okay, we are not splitting our data set into some training part and testing part, and then we are testing our model by using some testing data set. But we are just using this data set for the testing process. In the plots, I will show you here, these are our data points we have, and the model is also on the same data points we have drawn, on which we have trained our model. Okay. So one other aspect that we have learned that if we make our model or we are increasing the degree of polynomial equation, or we are increasing the degree of our model, okay, our model becoming more flexible, more complex, or more powerful, and it is very perfectly capturing the pattern or capturing the trend of each data point. Okay, so that we have learned in the last session. So in this session we will focus on overfitting and underfitting. What are these, and what are challenges, what actually these are, and how we can resolve that. And in the next sessions we will also see how we can overcome the overfitting actually. Okay, so here we will just get some understanding about the overfitting and underfitting of regarding models. Okay, if you can recall in the first sessions, introduction to machine learning, we have learned a little bit about the challenges regarding models, and we have seen that if I will show you, these are the same data points that we have learned there. Yeah, these points are same that we have learned there. That data is basically, we can say that data is a combination of information plus some noise, and our challenge is to identify the information content but distill away the invoice. Okay, so for that purpose we usually use the train test approach. Okay, we split our data set into some training part and testing part, then we train our model on the test by using training data set, and test our model by using test data set. Okay, so if the model we finish up with ends up, and you can say that if model also model the noise as well. Okay, we are trying to model the information, but our model has also capture the patterns of noise as well. Then we usually call that we it is overfitting the data points. Okay, the model is overfitting the data points, and of course it's bad for prediction. Second point for underfitting is that if it was not able to capture the pattern of the all information, then we usually call that our model is underfitting the data points, and again it is bad for prediction. Okay, these 2 points we have discussed. Now we will go in the detail of overfitting and underfitting. Okay, okay. So here, uh, uh, in the future, why we are doing this modeling and machine learning. Machine learning, the main purpose of machine learning is to predict about future, predict something about the future by using your present and past data. Okay, you have to generalize the information that will happen in the future by using the information that you have now. Okay, so in the future you have this type of information and you want to generalize this information, or you can say you want to estimate this information by using the information that you have now. Okay, so the data, the overall data, or the total data set that we have now is a combination of information plus some noise. Okay, so we should capture the patterns that are in the information, not in the noise. Okay, because noise are like exceptions or garbage. So if we will also capture the pattern from the noise, then we will not able to estimate properly the information that will happen in the future. Okay, the noise will occur in the model also. So we should uh, generalize our model in this way that can estimate about the future. Okay, if we have total data set, let's say we have splitted our we have a training data set and we are training our model. So we make our model in this way that model can capture the patterns from the training data points, not all the exceptions, or not every exception it has to learn. Okay, it has to learn some general patterns, not all the exceptional points or outliers also. Okay, so this is our aim or goal. Okay, usually in machine learning. So if I will show you this plot, here you can see there are two plots I am showing here. The same data points are here and the same data points are here. Okay, in this case the same data points, in this case the same data points. This is one model and this you can say the second one. Okay, this is second one model. So here you can say on these training data points, this model is generalizing the training data points, not actually in this case the model is not capturing each point perfectly. Okay, it is generalizing the trend of the data points that we have during our training. Okay, so on the other side, if we will see this model, here the model is trying to capture each pattern of or trend of each data point. Okay, and it has led to a very complex model we have here. Okay, which is very complex, or you can say very non-linear model we have here, and it is capturing the all the points very perfectly. Okay, are the training points. Okay, keep in mind we are doing here training, and this model we have achieved here due to training, and we are these are the training data points. Okay, these are the training data points. So in this case you can see, if I will give you an example, the trends, and if I will say that these data points or this type of trend can repeat in future. If I will ask you that this type of trend of data points can repeat in the future, you can say that of course this type of data point should repeat in the future. But if you will see this one, this pattern, if you will see this pattern, uh, there is very few chances that this type of pattern will again repeat in the future. Okay, it is exactly the same as the example I have mentioned here. Like the example, if I will say that Ronaldo made two or more goals in each match, if I will zoom here. Okay, okay, if I will say here you that Ronaldo made two or more goals in each match in last five matches. Now, there is a chance that Ronaldo again will make two or more goals in the future matches also. Okay, this is a general pattern, and we are generalizing that two goals. There is a chance that Ronaldo can make two or more than two goals in the future matches. But if uh, you have designed your pattern, or you have extracted the pattern like that, Ronaldo has made his first goal in the first 10 minutes and second goal after 34 minutes of the match in the last five matches. Okay, so you are overestimate, or you are perfectly capturing the pattern from each data point, and you are saying here Ronaldo has made his first goal in first 10 minutes and second goal after 34 minutes of the match. In last 5 matches he has followed, Ronaldo has made in this way. Now if I will ask you, there is a chance that in the future matches, Ronaldo again will follow that pattern, that he will make his first goal in the first 10 minutes and second goal after 34 minutes of the match. You will, of course, you will say that this statement can be repeated, but there is a very less chances that this statement will repeat, or this trend will repeat in the future also. Okay, because you are here overestimating some data points, overestimating the data that you have now. Okay, so you are also capturing the some exceptions also. Okay, so we have to design such a model that should generalize the future. Okay, you don't have to overestimate the points, because in each type of data we have some exceptions, we have some noise. Okay, so here in this case you can say this model is overfitted. Okay, because it is captured all the training data points very perfectly. Okay, so here this model you can say type of you can say this model is a good one. Okay, you can say here in the in the last session of polynomial, you have seen that in degree 6 case of polynomial regression, your model has perfectly captured the points, all the points, and you are getting 100% score. But it is giving you 100% score on the data points that it has seen during its training process. If there will be some new data point that will be in the future or in the real world scenario, if there will be some new data point that it has not seen during its training, and we ask this model to predict about that point, maybe it will give you a lot of error. Okay, the reason is that it is not generalizing the pattern. Okay, instead of that, if like these type of models that are generalizing, of course they have some type of errors, like this degree 2 is also good one, degree 3 is also type of good one. They are giving you error on the training points also, uh, not overestimating each data point here. Okay, so these type of models also can work good in the future also, because they are generalizing the data points, not perfectly capturing the data points. Okay, so here a little bit example, and you can keep in mind the example of like I have mentioned here. It's just to take the concept that we have to generalize about the future. If we will overestimate our on the data set that we have right now, then we cannot predict properly about the future. Okay, so now we will see how we can do that stuff practically. Okay, so usually we have this type of data set. We have this type of data set, original data set we have. Then we split our data set into some training part and testing data part. Okay, testing data set we usually say. Then we train our model by using that training data set, and then we evaluate our model on the data points that it has not seen during its training, and we can say that on the test data points. Okay, now we usually have, when we have trained our model, like we have trained this model on the training data set, then we usually have two type of errors. We can get two type of scores, or you can say two type of errors. Okay, like this model is trained on the training data set. Okay, this is both these models are. Now if you will pass the training data points to that model, training data points, and of course model will give some prediction, and if you will compare this prediction with the true values, you will get some score, or you can say you will get some error. Okay, how far your predictions are from the true values, this will be your error. Okay, so you can say that errors on training data points or training data set. Okay, the data set that you have used during your training. Okay, you are using to evaluating, or you are using the same data points during for the evaluation of model. Then if you will get some error, you will say that this is error on the training data set. This is the error on training data set. Okay, now if you evaluate your trained model by using the data points that it has not seen during its training, like test data points. Okay, if you will feed the you will pass these data points as an input to the model will give you some prediction, and you will see how far your predictions from the true values. Okay, you will get some error, and this error will be error on test data set. Okay, test data set. You can also define in the same way a test data set is the data set that it has not seen uh, during the training of model has not seen. Okay, you got usually two type of errors: error on the training data set that it has seen during the training, error on the test data set that it has not seen, or you can say the model has not seen during its training. Now here the point, the more technical discussion is here. If your error on training data set, if your error on training data set is high, and then error on test data set, of course, if your model is giving high error on testing data set or training data points, then of course it will give you high on the test data set. It means actually in this way, like if your model is not properly trained, okay, because it is giving you a error on the data points on which it is trained. Okay, on the same data point that it has seen during its training, if it is giving some error, then of course it will give you an error on the points that it has not seen during its training. Okay, so if error on training data set is high and error on test data set is also high, then you can say your model cannot capture the patterns of the data. Okay, it was not able to capture the patterns of data that you have for your training. Now what can be a reason here? The reason is can be this, like if uh, like I have told you last time also, that your data set also have some complexity, some relation between independent variables, and dependent variable have some relation with each other. The relation can be linear, the relation can be quadratic, the relation can be any type of polynomial type of, or any type of non-linear relation the your data set have. If your model is not able to capture, or model is not so much powerful that it was not able to capture the patterns, capture the trend that your data set have, then it will give you an error on the training data points, very high error, and on the testing data points. Okay, and also you can say the example here, like I have mentioned, data, if your data is quadratic, like your data points are like that. Okay, you have like that data points, okay, here, and your model is linear. Okay, your model is like that, then of course whatever you can do, how many data points you will feed during the training part, it will give you an error. Okay, because the model is linear you are using here, but your data is quadratic. Okay, so it will give you high error on the data points, and also it will give you high error on the test data points. So that case we usually call as under training. Okay, we usually call that our model is under trained in that case. The reason is that we are using the less powerful or less complex model for our data set. Okay, model has some more complexity, but our model is not so much powerful that it can capture that patterns, or that type of complex pattern from the data. So this is one scenario, that if we have high error on the training data set, and if we have high error on the test data set, we can say our model is under trained. Now second scenario is if our error on training data set is low, and if our error on test data set is also low. Then of course, if we are getting low error on training data set and test data set, of course the model is optimal. Okay, this type of model that we usually want, that we should give less error on the training data points and also less error on the future data points or some test data points. Okay, so we can say that this type of model is optimal. So we don't we actually we are uh, in the way of to find that type of model. Okay, so there is no problem in that type of case. We are good to go here. Now this third scenario can be here if your error on training data points is low, but your error on the test data points is very high. Okay, what can be happen here? Now you can say here your model has captured all the patterns in your training data set, all the patterns in your training data set, and also noise. Okay, so you can also noise. It has captured all the training data points perfectly. Now cannot able to generalize about the future. Okay, it has captured the patterns very perfectly during its training. That's why it is giving you a low error on the training data points, but it is not able to generalize about the future or test data points that it has not seen during its training. So that type of scenario we usually call overfitting or overtraining. Here you can say overfitting, or you can say overtrained on data points. I will remove that here. Okay, you can say that the model is overfitting the, or you can say overtrained on the training data points. In the same way, you can instead of that, you can write in this way. Sorry. Okay, you can write here overfitting. Okay, and here also you can write underfitting. Okay, so that you will not confuse by these terms. Actually, these are the same terms, under training and overtraining. But again, third scenario is that if you are getting low error on the training data points and high error on the test data points, then you will trap into the overfitting of the model. Now, maybe you are saying that there can be some fourth scenario. No, there will be not fourth scenario. If you want to see that, it means that your fourth scenario is like you have high error on the training data points but very low error on the test data points. So it is not really possible. You can say it is very impossible that how you can say that your model is not trained but giving you predictions about the future very well. It's impossible. Okay, so we will, that's why we will not discuss the fourth scenario. There are only three scenarios that we will face. One scenario is that when we have our optimal model and we are good to go here. One scenario where we have under training, this part where we have sorry here, where we have this part where we have under trained the model, and the one scenario where we have overtrained our model. Okay, we are in between these three scenarios usually. Okay, more technically, you have seen that how you can prove that model is overfitted or underfitted. You can do by using train test split. Okay, this is actually train test split, and you can calculate the errors for that. Um, it is more technical wise, the definitions of overfitting and underfitting as compared to just these definitions that we have discussed during our introduction to machine learning. Okay, data is equal information plus noise. So if your model is also has captured both information and noise during its training, then it is not able to properly estimate about the future data points. Okay, now what if we have these type of problems? Okay, we have this type of underfitting, overfitting. When trained, we are good to go when we have low training error and testing error. But when we have underfitting, what we should do? Okay, In the case of underfitting, the problem is that we have data and our model is not capturing or not able to capture the pattern from the data properly. Okay, like I have given you example that my data points are here uh, quadratic, but my model is linear here. But now it will give undertrained. Now you can say that your model is undertrained. Okay, in that case you should use the some complex model instead of just this model. Okay, you should use some sort of complex model, or if you are using some non-linear model, you have to increase the degree of your polynomial model. Okay, you have to use more complex model to avoid that underfitting of your model. Okay, in this way you can solve your underfitting. In the case of overfitting, how you can solve overfitting? There can be two type of problems: the problem regarding data, the problem regarding model. The problem regarding data is that if your model can be overfitted to the training data points if you have very less number of training data points. So in that case, you have to feed more data points to avoid overfitting. Okay. Now the second option it can be here that your model is overfitting here can be is is due to complexity of your model. Okay, you are using very complex model during your training. That's why your model trapped into the overfitting. So you have to decrease the complexity of your model. You have to decrease the complexity of model to avoid overfitting. Now this part we will discuss how we can decrease the complexity of the model. Okay, we will discuss in the future session. But in this session we will see the in more detail how by increasing the complexity of model we fall into the overfitting. You have seen in the last session, like when we are increasing the degree of polynomial, our model is capturing the patterns perfectly from the training data points. Okay, but what will be the behavior of this type of model on the test data points? So in that case, we were having just 6 data points. So in today's session, we will see a code in which we have multiple data points and we will split our data points into training data points, testing data points, and then we will try to analyze how by increasing the complexity of model we are falling into overfitting the model on training data points. Okay, now before going towards the code part, I want to elaborate here just two terms here: bias and variance. Error on training data set, you can usually you will say that this is bias. Okay, the error, the type of error that is associated with the training data points, we usually say bias, and the error associated with the training data points we usually call as variance. Okay, keep in mind for now just this. Okay, and we want such a model which has low bias and low variance. This type of model we usually have want, and this type of model we say that the model is optimal if it has low bias and low variance. Okay, now just some of you will see these type of terms in the future also, so it is important to discuss it here. So bias is same that I have discussed here: error on training data point and variance, error on the test data points. Now you can see here the bias is the part of generalization error. If I will zoom this here, you can see these type of terms. So bias is a part of generalization error is due to some wrong assumptions, such as assuming that data is linear, but actually the data is quadratic. Then high bias model is most likely to underfit the training data points. Okay, if you have high bias, it means you are also getting error on the training data points. So your model is most probably you are trapped into underfitting of your model. Now the variance is due to models excessive sensitivity to small variations in the training data. It means that your model is also capturing the exceptions noise as well during your training. Okay, so here they have mentioned very well that models excessive sensitivity to small variations. Okay, it is also capturing the very small variation of your data points during the training. So, or you can say in other word, a model with many degrees of freedom, or such as model which is high degree polynomial model, is likely to have high variance, so thus to overfit the training data points. Here you can see this model is this type of model here. This type of model is excessive sensitive to small variations as well, but it is ignoring the small variations. This model is ignoring the small variations. Okay, it is just generalizing the points, but this model is uh, excessive sensitive to the small variations also. Now we will move towards the code of today, in which just we will see how the with the increase of complexity of model trap into the overfitting. Okay, so before going to the part of Jupyter Notebook, I want to elaborate here the code, how the structure of code that I have implemented on the Jupyter Notebook. So I have here the dataset that I will use here will be just two columns. One column will be independent column, this one. This one will be independent column, and this column will be dependent. Okay, this one, and miles per gallon. You can say the weight is X, and miles per gallon is Y. Okay, so total we have 100 rows. We will have 100 rows in our data set. Okay, so first X, I will use first standard scaler to scale down my weight values. The reason is that I have to use some polynomial model, and when I will take the power, the higher power of that weight values, like the weight values of weight are added in the form of thousands, like 3504. So when I will take the power of 3504, the power 100, it will give you a very, very large value, which will be like a 2.86 into 10 raised power 354. Very, very high value. So to avoid these type of high values, I am just scaling down my weight feature by using standard scaler. Okay, then I will split my 100 data points into training data points and into test data points. Okay, now we will have x train, y train for training data points, x test and y test for the case of testing. Okay, now I will do x train if as I have to use some polynomial model, so that's why I will convert my x train into polynomial features. Then as I am converting my x train into polynomial features, so my data is here is a little bit skewed. But when I will take a polynomial, I am taking the powers of that skewed data. Then I will fall into a very high skewness. So to avoid the skewness, I will again use a power transformer to normalize my data points. Okay, then I will feed this X train after the polynomial featuring. After the polynomial featuring and power transformer, I will feed this X train to my model, and here Y train as it is to my model to train my model. Okay, after the training part, if I have to see the error of error on training data points, I can feed this X train that I have converted here polynomial into polynomial, and after the power transformer I can feed the pass as an input to that trained model, and it will give me some prediction, and I can compare these prediction my true values which are actually Y-train, and I can get the error on the training data points. Okay, or I can calculate the score on the model's score actually according to training data points. If I have to check on the test data points, then I will first I have to convert my x test into the polynomial feature, and then I have to transform it into the same scale that I have used during my training part into power transform dot transform we'll use here, and then I will pass as input to my trained model, which will give me some predictions, and by using that predictions I will check the model's score on the test data points. Okay, this structure I will follow in the code. So I was thinking that I have to explain these points before to explain the code. Now the purpose of code is just to explain how by increasing the polynomial degree our model will trap into overfitting of the model. Okay, so moving on towards the part of code. Okay, now here you can see some of the important libraries, and you already know about these libraries I have imported here. The original dataset I have here, in which there are multiple columns here. Okay, so I for the simplicity, for that case of explanation, I will just get two columns, miles per gallon and weight, as a df2. Then I will just for again for the to get the just the concept, I am using that data set. So I am considering just 100 points here. Okay, then I am just checking the type of my data, then how many unique values in my data, then correlation here. Okay, so how much correlation the weight has with weight actually independent variable, and mile per gallon is dependent. So it has 92 0.92 relation with the mile per gallon, and in the negative direction. Okay, you can say negative correlation it has, and you can also see by the pair plot that as weight is increasing, your miles per gallon are decreasing here. Then I will split my data set into independent variable x and y, which will be a dependent variable. Then I have used the standard scaler, and I have explained you to the purpose. The purpose is to just scale down the values because the values in the weight are very high in the form of thousands. Then I am splitting my x, y. It is x2 and y. X2 is just after the standard scaler. So I am splitting my data set into x train, x test, y train, y test. Okay. Okay, so here I am using scalar dot inverse transform to use for plotting, because when I have to plot some graphs, so I want to use the data, the input data, x data, independent variable, as which is unscaled. Okay, I don't want to plot my graphs on the scaled data. I want to plot my graphs on the original data I was having. So that why I am just inversing my transform that I have used here scalar dot transform. I am here using scalar dot inverse transform on the x train part, and also x test part. I am getting here two x train unscaled, x test unscaled. Okay, so that I can plot my graphs. So first of all, I am using a linear model, and by using linear model, you have seen that I am testing my score on the x train and y train. It means I am testing here my model and checking my model's score on the training data points. It is giving me 0.85, which is good. And on the score on the test data points also 0.87, which is also good. So linear model is also good in that case. But of course, we want some more accuracies in real world scenarios. We are going towards the models that are good, or you can say that are best in our case. So here, this is the linear model, and these data points that we have training during our training. The model is on the training data points. This is the model on the test data points, the linear model. Now I am going to use polynomial model, in which first I have to find the polynomial features for the degree is equal to 2. Then I am using a power transformer to normalize my data points. Then I am doing a training of my model, and here I am testing my model's score on my training data points, and you can see here as I have updated my polynomial degree. My score on the training data points is updated here, and it becomes 0.90 from the 0.85. Now on the test data points, it is also giving the same type of score 0.909, okay, which is also quite good. If we will see the model on the training data points, it is not linear, it is some sort of non-linear. Here you can see, and the model on the test data points. You can see here when we are giving the more power to the model, and model become non-linear, and it can more properly can get the patterns from of the data and can generalize the trend of the data. Okay, now here we just want to elaborate why we are using power transformer. Okay, besides this session, but here it is important to elaborate because of when I was using the standard scaler. Okay, after standard scaler, when I have used the higher powers like polynomial features, I have and I have to use like a degree is equal to 20. Then, if my original after original scale data points, standard scalar data points are have some skewness. Then, after after taking powers, my polynomial features will have high skewness. Like if I will show you here, if my original x1 have skewness minus 0.05, then as we are going down and taking high powers, my skewness is increasing. Like in the case of x raised to the power 8, we have 3.33. In the case of x raised to the power, we have 4.49. When we have x raised to the power 20, we have skewness 5.61. Okay, as power is increasing, skewness is also increasing here. So just for the sake of to decrease the skewness, so that we have to pass these features as a to the linear regression. And linear regression, I told you, these type of models are sensitive to the skewness type of data. So to remove that type of skewness, I am using a power transformer. And you have seen here, after using power transformer, our skewness of data will decrease a lot. Okay, all the polynomial features have the skewness less than 1. Like here it is 0.01, 0.025. Here you can see in the case of x raised to the power 20, we have 0.5. But in the case of before the power transformer, we have 5.5 almost. Okay, so that's why I was using here power transformer, because skewness, linear models are sensitive to skewness. So come back to our today's session. So we have used here, we have updated our linear model to polynomial model, and we have seen that our score on training data points and score on testing data points, score of model has increased. Okay. So here I, in the same way, in this by following the same structure that I have here, okay, by using the same structure, I have designed here a function, okay, so that I can plot multiple degree plots at once. Like I have run here a loop, and here I am calling my function 20 times, and here I will see the degree, the results of my polynomial models. Okay, so like polynomial model with degree 1, which will be of course a linear, it is giving 0.84, and the score on test 0.86. Now you will see, as we are moving towards and we are increasing our degree of the model, our model become more powerful, more complex. Our complexity of the models will increase. As complexity of model is increasing here, my score on the training data points, score of model will be increasing. Okay, and score of testing data points will be decrease or will decrease. You can see here from polynomial model with degree 2, it is giving 0.9. Model is giving score 0.9 on the trained data points and 0.909 on the test data points. Now in the case of, let's say, polynomial model with the degree 6, it is giving score on the trained data point 0.9. Now on the score on the test data point is 0.89. The score on the test data points start to decrease. When we will move more towards, like let's say in the polynomial degree uh, is equal to 18, let's say here. Polynomial model is with the degree 18, it is giving my me the score. Model has score 0.91 on the trained data points, but it has decreased the score too much on the test data points, and which will become less than 0. Here you can see the score become less than 0, -3 something. Okay, our model, as complexity of model is growing, model is learning the data points very well and becoming weird on the test data points. Here in the case of polynomial with degree 20, it has given model as score 0.9 on the trained data points and -79 means very low on the test data points. Here you can see the by the plots that how the model is behaving on test data points and the model is behaving on the data points and test data points. Okay, so here the linear model is behaving same type on both data points. Degree 2 is also behaving the same type on data points, and as you are increasing your model degree, you will see that you will analyze that the model's behavior on test data points will change drastically. Here you will see, like here your model is become in the case of degree it become more non-linear, and till now it has same type of uh, trend or same type of pattern on the same on the both data sets. Training data set, this is training data points and these are test data points. Okay, so till now it is giving the same type of. Now here you can say model is on the test data points, it's the same. It is improving on the test train data points, but it becoming weird on the test data points. Here you can see. Now as you will go down, you will see here, like on the training data points, your model is becoming good and good, but on the test data points, it becoming weird as your complexity of model is growing. Okay. Now if you will see the model which has polynomial degree 100, it will of course have 100 coefficients. Okay, because it has 100 columns during its training. 100, one column, originally it has just one column, weight column, and after polynomial features and degree using 100, it will get a lot of like 100 features here. Polynomial features, one just one intercept. Now you will see the score on training dataset is increased to 0.98, but score on test data point is very bad here. -4.8 into e raised to power 28 means it is very large in the large but negative in value. Okay, it become very weird, and you can also estimate by the mean square error. Like I told you, if your model is bad than the just a average model, like I explained into you in the case of R when we are discussing R squared evaluation metric, in the part of evaluation matrix of regression model, I explained you if your model is giving bad score, then the simple model which is y bar, which is just average model, then you can say that there is some problem in your model. Here you can see your variance is 33.76, but your mean squared error is 1.62 into 10 raised to power 30, which is very high, and your score is again calculated in the same way, 1 minus MSC divided by variance. Okay, you here you can see that your model has trying to capture the pattern of training data points very well, but it become very weird on the test data points. In the case of model with having a 200 polynomial or 200 degree, you can see here it again is very well and very perfectly capturing the patterns by going towards each data point, or you can say becoming very, like here we have mentioned in the case of variance, we have mentioned that part due to model's excessive sensitivity to small variations in training data points. So here you can say it become very sensitive to small variation to training data points. So here you can say it is your bias or your error on the training data points is decreasing, but your variance is very high here. Okay, as your model is growing up, you have seen that till now, as your model's complexity goes towards upward, your model become uh, good on the training data points, or you can say your bias becoming low, but your variance is becoming high. Okay, so if you will see the scores, just I have here the data points. You can see the code also by yourself. It's not a big deal. Okay, so here just the my aim is to explain you the concept how by increasing the degree models, the overfitting of model increased. Now I will show you a Excel file that I exported here, in which I am here mentioning the degree is increasing. Then the what is the behavior training score, testing score, and mean square error on test data points. Now here you can see as your degree will increase, your score on training data points will increase, score on testing data point will decrease, and mean square error will also increase. Okay, as you will go down, you will see that your score on training data point becomes 0.98, score on the test data point become less than 0, and the mean square error will become very high. As you will go down, your score will keep on increasing on training data points, score on test data point become keep on decreasing, and your error is increasing. Okay, error on test data points. Okay, so so till now we have discussed that how in the code also, that how by increasing the complexity of your model, you are going towards the part where you are overfitting the training data points, and you are falling into some model that is very bad for the prediction. Okay, now uh, here is in the next session we will discuss how we can avoid overfitting. Sometimes you fall in a situation in which you have, when you will use simple model you will have a underfitting problem. When you will use some complex model you will fall into problem of overfitting. Okay, how you can get a some optimal model, and optimal model will lie in between that. Okay, in between simple model and complex model. Okay, optimal model lies. So we will artificially try to decrease the complexity of model. Okay, we will try to decrease the complexity of model so that we can get some optimal model. Okay, we will try to decrease the artificially decrease the complexity of complex model, so that we will, complexity in this way we will reduce the complexity of model, that we will not fall into undertraining of or underfitting of the model. Okay, we will decrease the complexity in this way. There are some techniques we will study or learn in the next sessions hopefully. So maybe you will ask a question that instead, if we have overfitting, we should use some simple model instead of some higher degree polynomial model. Yeah, some in some cases you can directly get use, but in some cases when you are using some simple model, you are falling into case of underfitting. When you are using some complex model, you are a little bit complex model, you fall into the overfitting problem. Now, how you can tackle them? You have to use some technique that in this way you will reduce the complexity of your model, that your model will not fall into underfitting. Okay, so this part we will discuss hopefully in the next session. So I hope that this session will be very interesting for you and you will learn a lot. So for now, thank you.